Okay, so we have this example in the practice problems, and they tell you try this example utilizing the steps, which is a little bit unfortunate for reasons we'll get into in a second. They say a round plant is crossed with an unknown plant. So hit pause for a second here. What they're talking about once again is the pea plants. So to remind you how that works, because we have to do a legend first. A pea plant that produces round peas that look like a green little ball has the big R allele. That's the allele for round peas. And if you don't have that, then you have the little r allele, which causes you to produce wrinkly peas. And so the three pea plants that can exist are big R, which is homozygous round, big R, which is heterozygous, but because round is dominant, here the peas still come out round. Or if you have a plant that's little r, then that will actually produce wrinkled peas. So there's our legend. I'll shrink that down a little bit, scoot it over to the side. Okay. So, parents' genotypes. A round plant, one of the parents is round, and it for basically all of this stuff until we get to sex-linked traits, it doesn't matter which thing is the father and which one is the mother, so round plant is good enough for us. Is crossed with an unknown plant. Is this enough for us to do the parents' genotypes? And the answer is no, it's not. So we're going to go off the rails pretty quickly with this question and not be able to follow these steps, unfortunately. But we can still crack this. It's just going to take some problem solving and some improvising that maybe we're not quite warmed up for yet, but we'll survive. So here are the problems. First of all, we have an unknown plant, so one of our parents we don't know a thing about. We don't know if they're big R or big R or little r. There's just zilch. The other plant they tell us produces round peas, but even that is not very firm because either one of these produces round peas. So the plant that produces round peas is big R, don't know. It could be big R, or it could be big R. You'd get round peas either way. That makes sense? So we know that about one of the parents. We know nothing at all about the other parent. And they're telling us for the offspring, they got 50% round and 50% wrinkled. And from that, we're supposed to fill in all these blanks. Tough one. Is there a way we can figure this out? Can we do some trial and error or some kind of thought experiment and work out what's going on here? Okay. If you're still thinking about that, hit pause and finish your thought, but I'm going to start throwing out some ideas of my own here. First of all, what are the two things that could be in this spot? For this parent, we could have either their big R, or their big R, right? They have to have one big R because they produce round peas. So either one of these things is possible. And for the other parent, we could have big R, or we could have the heterozygous, or we could have the double recessive. Right now, oh, sorry, I shouldn't say X there. That means something else. I want the word or there. So in theory, all of these are on the table and both of these are on the table. But if this parent was big R, what would that mean? If you're big R, then every one of your offspring gets the big R allele from you. And as soon as an offspring has big R, automatically they produce round peas. But some of these peas are wrinkled, which means this can't be true. If you are big R, then every single one of your offspring is going to get the dominant allele from you, and they're going to show the dominant trait, because that's what dominant means. It means if it's there even once, it takes over. So this parent cannot possibly be big R. They must be heterozygous. Big R is impossible. If it were, the offspring would be 100% round plants. So that takes care of one parent. We know this first parent must be, whoops, after all that I almost wrote the wrong thing. This parent must be heterozygous, one of each. How about this parent? Can we do anything like that to narrow this down? Well, first of all, this parent, for the same reason, can't be big R. If they were, there'd be no, they wouldn't have any wrinkled seed, any wrinkled pea plant offspring. So that one can't be right either. So now we're down to two of these. This parent could be big R, or they could be little r. Right this second, I can't think of a clean way to tell you which one it is, but one option that we have is to just try them both. And let's see which one makes sense and which one doesn't. We know one parent is big R. What if the other parent was big R also? Big R cross big R. What kind of offspring does that give us? So what's happening here is when I get to these steps, I ran into the parents' genotypes and went down in a ball of fire here because I didn't know anything about them. But what I'm doing now is saying, okay, well, let's take some guesses at the parents' genotypes just because that'll allow me to progress. So I'm going to take this hypothetical pair of genotypes and we'll see if they lead us to 50% round, 50% wrinkled. And if they don't, I'll try another combination and hope that that works out. So at least this gets us kind of back on track with our progression. Set up a Punnett square, did it already. Get the parents' gametes on there. This parent will produce big R half the time, little r half the time. And this parent, exact same. Big R, little r. So for offspring, that gives big R. Here we get big R, little r. Here we get little r, big R, but don't write it that way, dominant first. And here we get little r, like so. What does that give us for phenotypes? Round, 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 wrinkled. What do you think? Is that it? Well, we're looking for a combo that gives us half round and half wrinkled, and that isn't this. This one is 3/4 round and 1/4 wrinkled, so apparently this is the wrong combination. So, unfortunate, but let's try something else. We know the one parent has to be big R, little r. The other possibility is the other parent was double recessive. Let's see if that works out. What if it's big R cross little r. Will that give us anything that makes sense? Let's see. This parent can produce or can pass on the dominant allele or the recessive allele. This parent can only produce the recessive allele, so really that's all we need to put here. You remember our earlier example where we had a shortcut where we only wrote, we had the same allele twice and we only wrote it one time because the only thing this parent can pass on is little r? That's what I'm doing here. Now, that gives you a Punnett rectangle instead of a Punnett square, but that's no big deal. It's fine because it's still representing everything that can happen with these two parents. This parent is a 50-50. We've got both of their possibilities here. This parent is just absolutely guaranteed to pass on little r alleles, so that's all we draw. And that means there's only two possible offspring here. One of them is big R, little r. The other is little r. That means half the offspring are round, half the offspring are wrinkled, and hooray, that's exactly what we were hoping to find. So, for this to make sense, the parents had to be one of them heterozygous and one of them homozygous recessive. This is kind of a tricky question, and I feel a little bad that it comes up this early in the practice because I don't feel like you're warmed up enough to deal with this kind of thing yet, but at least now you've seen it, and when we see it next time, I think you'll know what has to happen. So these steps still hold up, and when you get to here and it says parents' genotypes, If you can't find them, then you kind of have to do some guessing or do some hypotheticals and start trying combinations because you really can't move on to the Punnett square or any of the other steps until you've got parents' genotypes, or at least a guess at the parents' genotypes. And working with those, we were able to finish this thing.